Okay, in the previous classes, we were discussing about the memory interfacing. So, how we interface the memory with the microprocessors that we have discussed. So, in this lecture, we will discuss about interfacing the input-output devices with the microprocessors. Okay. So, for interfacing input device such as a keyboard or interfacing output device such as a LED display, so this depends on which instructions are basically available for data transfer between the processor and the IO devices. So the microprocessor 8085, we have two instructions. One is out and one is in. So these two instructions, they are used to transfer the data between the processor and input-output devices. Okay. So out instructions is used to display the contents or to transfer the contents of accumulators to the output device, which is identified by basically a 8-bit address. So along with this instruction out, you have to write a 8-bit address, so that 8 can be address can be anything. Suppose it is out 8th. Okay. So this is a 2-byte instruction, of course. It will have its opcode, and that is, the opcode is fixed for each instructions. Only the operand can be modified. So the opcode for out is D3. Okay. So whenever the processor fetches this instruction, 8-bit code D3 from the memory, it comes to know that it has to display some contents from the accumulator onto a output device. Okay. Now to which output device those contents are to be transferred, that is also specified along with the instructions in the form of the address, which is a 8-bit address, which is called as basically port address. Okay. So if you write instruction out in 0h, so the processor will do, it will transfer the contents of accumulator to a port which is basically having address of 80h. Okay. So when you store this instruction in the memory, so you need two bytes, one byte for opcode, of course, and the second byte for the operand, which is the 8-bit address in this case. Okay. So at one memory location, we will first store D3, which is the operation code, followed by the 8-bit address of the port on that device, which is suppose 80h. Okay. So this will be stored at some location, maybe 2080h. Okay. Similarly, the next instruction or this is basically this port address. It is stored now at 2081h. Okay. So if you store this 2-byte instruction at these two memory locations, okay. So when the processor will fetch the first byte, which is the operation code, that is D3, it will come to know that it is a data transfer instruction between the processor and a output device. Okay. And in the second part, it will fetch this port address from the memory. Okay. And in the third part, on the third machine cycle, it will display the contents of this accumulator onto this port with the address of which is specified in the second part. Okay. And similarly, we have this in instructions. So the format is same. So you have in, it has its own operation code, and the operation code for this is DB. Okay. So DB is a code for this instruction. So when you write the complete instruction, you have to write in along with the port address. It may be suppose 88h. Okay. So when the processor will fetch this instruction, this code. So again, it is a 2-byte instruction. The first is your operation code. The second is your 8-bit port address of the input device now. Okay. So whenever the processor will fetch this opcode db from this memory, so it can be stored at any location. Again, suppose it is located at 2070h and it is at 2071h. Okay. So the processor will fetch this opcode db from this memory. It will come to know that okay, it is a data transfer instruction between the input device and the processor. And then in the next part, it will look for this port address of the device. Okay. And in the third machine cycle, the contents will be transferred from the input port to the accumulator. Okay. So this is how this in and out instructions they are executed in the microprocessor. So these are the two instructions available in 8085 which are used for data transfer between the peripherals and the processor. Okay, so if you want to communicate between the peripherals, that is input output devices and the processors, you have to use these instructions in and out. And the question is, if you use suppose instruction out 01h, okay, it means I am trying to transfer the contents of accumulator to the output device, and that output device has the address which is 8-bit address, that is 01h. Okay, so this type of, you can say, input output connection or input output and device interfacing where the port is identified by 8-bit address, we call it as peripheral input output. Okay, another is your memory mapped input output, in which the device is basically identified by 16-bit address. Okay, so that we'll discuss later on. So first we will discuss this peripheral input output instructions, which is out and in. Okay. So since the port address is 8-bit, it means you can have 2 to the power 8, 256 different addresses. Okay. So the 8085 processor can communicate with 256 devices, you can say, at a time. Okay, because there are 256 possible addresses. So the port address, it can be, you can assign it from anything from 00 to FF. So how a particular device is assigned a port address, that will come in the next part. Okay, so that depends upon the again the external logic circuit which is available to you. Okay, so by using some external devices or external hardware logic, so you can assign any address to any particular port. Okay, but before that, let us see how this out and in instructions are executed, or will in fact discuss the timing diagrams, which will give you more clear picture. Timing diagram of, let us take this example, out instruction. Okay. Now you know what is the format of this out. So you have out with a 8-bit address. Suppose I take address as 80h. Okay. This is my instruction. And let us suppose we have stored the instruction at some memory location 2080 and 2081h. Okay. So at 2082, we have to store the opcode which is D3, and then at 2081 we have to store the 8-bit address which is 80 in this case. Of course, all these are in hexadecimals. Okay. Now the processor will execute this. So first your opcode will be fetched. So first cycle is of course your opcode fetch cycle, because that is the first part of any instruction. This will be your machine cycle M1. Okay. Once this opcode is fetched D3 from this memory location 2080h, the processor will come to know that okay, it is a 2-byte instruction. Then it will fetch the next byte. Okay. It means your next machine cycle is basically memory read cycle. Okay, it has to read a byte from the memory, which is now a machine cycle M2. Okay, so what is the next thought machine cycle? Because see, by using this 8-bit code, the processor only comes to know that it is a data transfer instructions and it is a 2 byte instructions. Okay, when the processor gets the next byte from the memory, it's a memory read cycle, and it is just a port address. Okay, so in order to transfer these contents of accumulator to that port, which is identified by this address, the processor has to perform one more machine cycle, which is basically input output write. Okay, this will be done in third machine cycle, that is M3. Okay, so first the processor will fetch the code. It will come to know that it is a 2 byte instruction and it is used for data transfer between the accumulator and the output device. Then it will get the address of that output device from the next memory location, that is 2081H. And in the third part, whatever are the contents in the accumulator, they will be transferred to that device, which is identified by this address. Okay, so you can see in now code fetch cycle, it requires 4 states. So memory read cycle, it involves three states. Similarly, your input output write operation, it involves 3 T states. So you need in total 10 T states for this. So your 3 machine cycles with 10 clock cycles or 10 T states for the execution of this complete instructions. Okay. So in the first 4 clock cycles, your output fetch will be done. In the next 3 clock pulses, memory read operation is done. And in the last three cycles, your input output write operation is performed. Okay. So if you plot this, it will be revision for you again for the support fetch and memory read machine cycle level. So you have one clock pulse, 1, 2, 3, 4. So this is one clock pulse. This is second, third. This is T4, 4 T states. Okay. This is T1, T2, T3, T4. So they basically comprise your machine cycle M1, which is basically in a way opcode fetch cycle. Okay, so this part you already know what has to be done now. Okay, so I'm saying that okay, my instruction is stored at 2080H and 2081H, and the opcode is D3, and the next byte is 80. So what the processor will do, it will first place the higher order address, that is A2, A15 on this higher order bits, and lower order address on the lower order bits in the first clock period itself. So higher order address will be placed on this, that is 2081. So 20H will be placed on higher order bits, and on the lower order 8 bits, that is A D0 to A D7, the processor will place the lower 8-bit address, that is 80. Okay, of course it doesn't have the decimal, right? So this address on the lower higher 8 bits, it remains for almost 3 clock periods, and then it is unspecified here. So what is next is done by the processor. So the first task is to place the higher and the lower 8 bits address on the higher and lower 8 bit address. And since this data bus is bidirectional, it has to be used for data transfer in the next cycles. So it has to be demultiplexed by this signal, which is ALE, address latch enable. So the address latch enable in the first clock period itself, it is a kilo signal to goes from 0 to 1. Okay. And before the end of this pulse, it again comes back to 0. So it will go from low to high, so that this lower 8-bit address is now latched. Okay. For the next clock pulses, it is used now as a data bus. Okay. And then this read signal, it gets control signal, which is the read signal, it gets activated in the second clock pulse. So it remains at logic 0 for 2 states almost, and then the processor again sets it to 1. Okay. At the same time, one more control signal, IO slash M bar, so since it indicates that it is a memory related operation, so it goes from 1 to 0 and it remains at logic 0. Okay. And of course, see, when we have discussed these control signals, we have seen that by combining this read signal and this IO oblique M signal, you can generate two separate signals. One is memory read and memory write, memory read and input output read using some logic gates. Okay. Similarly, by using this write signal and this IO oblique M signal, we can have two separate signals for memory write and input output write operation. Okay. So this memory read signal, it basically follows your the read signal. Okay. So this is combined using these two. So by combining the read signal and input output oblique memory this control signal, you can have separate signal for memory read operation. Okay. So whenever this read signal will go low and whenever your input output oblique memory is 0, so when both the signals are 0, then only this is activated. So that is why for this part it is 0. After this it goes to 1, it again goes to 1. So it basically tracks this read signal. Okay. So you have placed the higher order address on the higher order bits, lower order address on the lower order bits. The ALE signal goes 0 to 1. Your lower 8-bit address is latched. Okay. In the second clock pulse or T2, the read signal gets activated. Now, when the read signal gets activated, what happens? The data from your memory will be placed on this data bus. So the data on this memory is now my opcode is D3. Okay. So during this pass, so once you set this control signal, that is read, so the data from the memory comes on the data bus, and from the data bus it goes inside the microprocessor. Okay. Now since it is a 2-byte instruction, so in the last clock pulse, okay, this data bus goes in the high impedance state. Okay. If it is a 1-byte instruction, of course, the instruction has to be completed in the last cycle T4. Okay, but now since it is a 2-byte instruction, it has to wait for one more byte. In the T4 cycle of this machine cycle M1, the processor will interpret what has to be done with this. Okay. So this is one part output fetch. Okay, so your data byte D3 is taken from the memory inside the processor. The processor comes to know that it is a 2-byte instruction. So it will now take the second byte, which is 80H, placed at 2081. So it is a memory read operation. And in the memory read operation, you need 3 more clock cycles. So you have 1 clock cycle, then 2 and 3. This is, I can again write T1, T2, T3. But these T1, T2, T3, therefore now next machine cycle, that is M2, which is a memory read cycle. Okay. in the memory read cycle again, you know what has to be done. The processor will first place the next address is 2051. Okay, so it will again place 20H on this high rate bits. Okay, to place the lower order address, that is 2081. So 81 is placed on this lower 8 bits. Okay, again your ALE goes from 0 to 1. Since it is a memory read signal, so during this part, during the first clock period T1, your address is lower 8-bit address is latched. Now your data bus is free to carry the data for the next clock pulse. So when the AL goes from 0 to 1, address is latched. Then in the second T2 of machine cycle T2, again read signal is activated. So when the read signal gets activated, the data from the memory location which is selected, that is 2081H, and their data is 80, which is the port address. It comes on this data bus and it is taken inside the processor. Okay. Again, since it is a memory related operation, your input output slash memory it will remain at logic 0, and this memory read signal it will again go low here when the read signal gets activated. Okay. This is memory read cycle. So these two cycles you already know, okay, that we already discussed in the timing diagrams. Now what is the last cycle we have? Last cycle is now your input output write operation. Okay. So it again involves three machines, like three T states, 1, 2, and 3. So this is now my machine cycle M3, which involves again three T states, T1, T2, and T3. And this machine cycle is input output write cycle. Okay. So during this machine cycle, you know, the processor will transfer the contents of the accumulator to the output device, which is identified by this port address. Okay. So what has to be done again in this case? The procedure is same. Like we have memory write operation. It is very much similar to this. The only difference you will see is in this control signal, that is input output oblique, and because this gives the status whether it is the input output operation or memory related operation. So again in this part, now what will happen? The processor will again place the higher order address. Now see, now in this case there is one difference here, of course, because now here the address is not 16 bit. Now 80 second byte, it is a port address. Okay, so port address now here is 8 bit only. Okay, in the previous cases it was 16 bit. So previously it was 2080H, then 2081H. In the third machine cycle, the address is only 8 bits. It is 80H. Okay. So what the processor does basically, it places the higher as well as the lower order address both on this higher and lower order address bus. Okay. So both addresses are placed on this higher and lower order address bus, and then again ELE will be activated here. Your address is latched. So now the next part, this is free for data bus. Okay. Now since it is a write operation, so the read signal will not be used, but in place of the read signal, it will be a write signal. Okay. And along with the write signal, you have to set this now. This signal, control signal, will be set to 1, because since it is a input output operation. So at the start of this T1, the processor will set this signal to 1. Okay, which will indicate that it is a input output related operation. Okay, and now see, during the first clock pulse, that is T1 of this M3, the processor is busy latching the address, lower 8-bit address. Okay, so that it can be used for data bus in the next cycle. So then T2 of this machine cycle M3, the write signal will get activated. Okay, so you need one more signal here for this, which is write signal, because it is a write operation, not a read operation. Okay, so you have now here another signal write, which is a kilo signal. So it was initially at logic 1 because we are not doing a writing operation, but at the start of this T2 of this machine cycle 3, it will get activated. Okay, and of course you can generate a input output write operation by combining of these two signals, input output oblique memory and write signal, that you know how we do this. Okay, so this signal will again follow this signal. It means this will be get this signal basically gets at logic 0 when your input output slash m bar is set to 1 and it is set to write signal set to 0. Okay, so when this is 1 and this is 0, this is at logic 0. Okay, so this signal input output rates write signal will get activated. So if you have two separate signals for memory and input output, of course you can use this signal. Otherwise, you can simply just use the write signal. So write signal goes low. So after this, what will happen? Now, whatever is the data on the data bus, or whatever is the data in the accumulator, sorry, which may be anything. Okay, so that data from the accumulator will now come on the data bus at this point. So accumulator contains 8-bit. It will come on the data bus, and from the data bus it will be connected, which is connected to basically this output port or output device. So this data will be displayed on that output device. Okay, so this is what is the difference between this memory write and input output write. Okay, the difference is only in the control signals. So this signal will go from 0 to 1 if it's an input output related operation. If it is a memory read operation, of course it will go from 1 to 0 or it will remain at logic 0 for the entire clock pulse. Okay, so this is how this out instruction is executed. Okay, so during the first machine cycle M1, which is the opcode fetch cycle, the opcode, which is D3, it is fetched by this processor and it is decoded. So once it gets decoded, the processor comes to know that it is a data transfer instruction and it is a 2-byte instruction. And in the next machine cycle, which is a memory read cycle, the next byte, which is basically another port address, it is taken inside the processor. Okay, and in the third machine cycle, which is a input output write operation, the contents of the accumulator are displayed on that output port, which is identified by this address. Okay, so how it is done? The processor places the higher and the lower address. Both the addresses are placed on the higher and the lower bits. Of course, this information is non-redundant. You can just use any one of these 8-bit address to identify that device. Okay. So the lower and 8-bit address are both the higher and the lower 8-bit address bus is loaded with the same address, which is the port address that is fetched from the first cycle. So AL is activated to latch the lower order address that you know, and this signal input output oblique memory, the status signal, it goes from 0 to 1 to indicate it is a input output operation. And in the T2 of this last machine cycle, the write signal gets activated. Okay, so when the write signal gets activated, the contents from the accumulator, they are basically placed on this data bus. Okay, and now since the data bus is connected to this output device, so during the T2 and the T3, these two machine cycles, these two clock pulses, they are important. For these two clock pulses, the contents of accumulator are basically available on the data bus. Okay, so during these two machine cycles only, these contents has to be latched, because after once you write this instruction out port address, after this there has to be another instruction. Okay, then the processor has to execute some other instruction. But before you execute some other instruction, these contents has to be latched. Okay, so you'll see in the next class that During T2 and T3, we basically use a interfacing circuit or logic circuit which basically displays the contents of this accumulator on this port, which may be LED display or any other display. Okay. Now in case of out, if it might have an in instruction, okay, so the procedure is same. First will be output fetch, second will be memory read, the third cycle will be now input output read operation in case of write. Okay, so the only difference will be here. Now this input output slash m, if it is a read cycle, what will happen in that case? This input output slash m controls it will remain at logic 0, okay, for in instruction, because it is again a sorry no, this will this will be at logic 1 because it is input output operation. Yes, this write signal will not be used. In fact, again the memory read signal will go at logic 0 at the T2 of last mission cycle. Okay, so these two signals in that case will not be used. Write signal will not be used. Okay. Of course, the input output has to go from 0 to 1 to indicate that it is a peripheral operation, and the read signal can get activated. So the contents of, now in this case what will happen, the contents from this input device, they will be placed at the data bus. Okay, the data bus will take those contents inside this processor into the accumulator. So in the out instruction, the contents of the accumulator will be placed on the data bus, and from the data bus those contents will be displayed on a output device. So this is the difference in the timing diagram for input and output instruction. Okay. So next we will see that how we basically interface a device, a input or output device with the processor, and how we assign this address or how this address is used, 8-bit address is used to identify a particular port. Okay.